I'm going to be talking about K3 Continuum IS, Advanced Direct Detection for in-situ chemical analysis. What are the current challenges for in-situ experiments? So it's challenging to capture rapid or unanticipated events. Often we need to compromise between high speed and high resolution. And in all cases, the experiments are labor intensive for both data capture and data analysis. The results that we get strictly depend on choices that we have to make before the data is captured, and that's often with limited information. So how does a K3 GIF continuum help us, in particular for in-situ EELS and spectrum imaging? So the K3 is a low noise, high speed, high sensitivity electron counting detector. Because we're operating at high speed, that allows us to capture data at high time resolution, so we can avoid missing important sample changes throughout the experiment. Because of electron counting, we have no instrumentational noise, so we're just shot noise limited. This is useful for in situ as it allows us to oversample in time, so we can run faster than we need to, and then we can sum later without penalty. So we can kind of tune the time resolution or the in situ stimulus resolution that we need after we've acquired the data. The detector has a sharp point spread function. So why is that useful for EELS in particular? So sharp point spread detector allows us to maintain energy resolution at low spectrometer energy dispersions. This means that we can maximize the energy field of view and collect the maximum number of ionization edges at the same time. But we also, because we still have good energy resolution, we can do fine structural analysis. So we have lots of ionization edges, and we can do chemical state mapping, oxidation state mapping on, all of them at the same time. So many techniques, one system. It's easy to acquire across multiple modes. So with a single system, we can do TEM, STEM, energy filtered TEM, EELS, STEM diffraction imaging, STEM spectrum imaging, and we have user-defined acquisition frequency in all modes. So what does that mean? Essentially, in all of our acquisition palettes, we have a view button and a record button, so common modality across all of them. Two examples that we have here are our TEM imaging, so our kind of camera imaging palette, and then our scan palette. So we just define our acquisition frequency using this view button. And then when we want to start our in situ acquisition, we just hit record. And then in all of these modes, we have look back. So if you enable look back, essentially the software will start recording data, keep it in a memory buffer before we hit record. And that's really useful as it allows you to avoid missing important changes in the sample as the experiment progresses. So the purpose of this talk is really to focus on EELS and STEM spectrum imaging. So we're going to walk through a couple of application examples. First example is an EELS example. So we can continuously collect EELS data just like we record in situ TEM data. In this example, we're melting and recrystallizing tin nanoparticles over this temperature range, 50 to 250 Celsius. So what we're looking at is a live kind of in situ acquisition, so low loss spectrum. And we're interested in this tin plasmon peak here primarily. So as you may have noticed, during the course of that video, we were seeing a shift in this plasmon peak position, and that's associated with the melting and recrystallization of the tin nanoparticles. Second peak you see over here is the plasmon peak from the silicon nitride membrane, and these overlays that we have are fit windows for non-linear least squares fitting. So we have a Gaussian fit to this peak and a Gaussian fit to the second peak. So you'll see why that's useful in a second. So we have streamlined data processing and visualization. So very easy to process our EELS data to produce videos. So that's useful for presentations, cascade plots for publication, and we can plot fits or quantification results over time for analysis. So the fit that you see in the bottom right here is actually the peak center of the Gaussian that was fit to the tin plasmon, and you can see how that changes. So we've done a few kind of melting and recrystallization cycles here by heating, cooling, and you can see how that changes there. So all EELS processing works with all EELS datasets. So basically anything that you can do with non-IS data, we can do with IS data. It's also really easy to correlate holder data with the fit results. So what we're looking at now on the right-hand side is the holder temperature here, so the measured holder temperature. And then we have the plasma peak energy, so the non-linear least squares fit data. And you can see that correlates very well with the melting and recrystallization that I kind of already discussed in the previous slide. Okay, so that's our EELS example. And now we're going to move on to spectrum imaging. So spectrum imaging essentially is when we are acquiring a data cube with two spatial axes and additional analytical axes. So maybe EELS, EDS, or in the case of 4D STEM, we have diffraction data. So we're getting our spectrum image data just like we record in situ EELS or TEM videos. So this is quite a nice example. We heated copper oxide in vacuum over a temperature range from 100 to 540 Celsius. Because we're heating in vacuum, we reduce the copper oxide. So this is a one-shot experiment. The change is non-reversible. So it's nice for this kind of material or this kind of experiment to get all of the data at the same time. And we can do that by customization through scripting. So this is pretty cool. So we're getting EELS spectrum images, EDS spectrum images, and 4D STEM spectrum images, and then EDS again, because we can get the EDS with the 4D STEM data, we can get the EDS with the EELS data. So we essentially can collect our EDS signal for free, so we can collect twice, double our signal to noise ratio. Okay, so let's take a look at the data in a bit more detail. So first of all, if we take a look at the ADF signal, so the imaging data, you can see that there are microstructural changes in the particles that we're looking at over the temperature range that we heated over. So if we kind of take a look at this guy here on the left, at 100 to 140 Celsius, compare to the same kind of region of the sample at the higher temperature, you can see that it's completely changed. So there's obviously interesting things happening in this sample. We can look at the 4D STEM data, so crystallographic information. So the way that we've processed this data here, Ben Miller, my colleague, used the 4D STEM data to generate maximum spot maps using a custom Python package he wrote. If you're interested in the details of that kind of analysis method or technique, I'd refer you to the paper that Ben presented last year at the MMC conference. But we have the full 4D STEM data cube there, so you're kind of free to do whatever you want with that data. Okay, so that's imaging and diffraction covered. So let's move on to EELS. So we acquired counted EELS data in dual EELS mode with the K3 at the lowest spectrometer dispersion. So the lowest spectrometer dispersion is 0.9 EV per channel. That gives us an energy range of 3000 EV per spectrum, and we have two spectra. And we get a single channel full width half maximum. So our energy resolution is 0.9 EV. Dual EELS, so in this case, I had the low loss spectrum as one of this pairs, one of the spectra in that spectral pair. So we've got the zero loss peak, which allows for accurate energy scale correction or calibration. And we have the capability to do plural scattering correction, which is really important for samples where the thickness is changing. So this is a great example of that. So what did we do with our dual EELS data? So we're interested in the copper oxidation state. So it makes sense to look at the copper L edge. So basically looking at the copper L edge, you can see we have an RGB map here of our three kind of copper references or standards. So I'm mapping copper 2, copper 1, copper 0. If we kind of look at the RGB composite here, makes sense. At the low temperature, we have mainly blue contrast in the map, so that's majority copper 2. As we heat, we see some red kind of becoming more prominent, which is the copper 1 map. So we're reducing from copper 2 to copper 1. And then as we get to the highest temperature, we start to reduce even further. So we start to get some copper 0. Okay, what next? So we can do the same for other ionization edges in the field of view of our spectrum. So we took a look at the oxygen K edge. So this map here, so we have the yellow and the kind of the pink map. So we have yellow is the oxygen fingerprint for silica, and the pink is the oxygen K fingerprint for copper 2 oxide. So this is kind of nice. This shows us a similar sort of trend. So we see that essentially the pink contrast is most prominent at the lowest temperatures, and then slowly disappears as we reduce the copper oxide. And then we have silica throughout, which is quite interesting. Now, this is kind of fun. So because we have such a big energy range, we also noticed in this sample that we have zirconia or zirconium. So I was able to map the zirconium L edge. So we've got this zirconium particle or zirconia or something here throughout the whole experiment. We wouldn't really have seen that if we didn't have this big energy range, because the zirconium L edge is out at around 2200 eV. Blue contrast that we see in this map, it actually looked like there were additional oxygen fingerprints. So I've tried to map a zirconia oxygen fingerprint here. So so the blue is oxygen LNES fingerprint for what I think is zirconia, and the pink contrast is the zirconium L map. Okay, so this isn't the full story. This is kind of the interesting things that happen as the temperature changes, but we've got even more data. So we haven't even looked at the EDS yet. There's some extra stuff going on. So if we, let's just focus on just this one temperature step. So 280 to 320 degrees Celsius. So there's extra, like a whole bunch of extra stuff that we've got going on. So you can see the nitrogen K edge. We've got nitrogen signal very strong where the nitride membrane is, which makes sense. We have the copper K line in the EDS. That agrees very well. Our kind of copper K EDS map, it kind of backs up the EELS data that we saw from the copper L map. What else do we have? Okay, so we found that we have some titanium in the sample. We found that we have some iron in the sample. And we can verify this because we have the titanium L edge in our EELS data, titanium K in the EDS data, iron L in the EELS data, iron K in the EDS data. So this is really nice because we have the two analytical signals. They're showing us the same information. So it gives us a lot more confidence that this is actual, real information from the sample and not just some artifact. And what's kind of interesting here is that we were just interested in copper oxidation state, really. But because we have all this extra information, we can learn a lot more about the sample and the changes that are happening in the sample. And as I said, it's a single shot experiment. So it's important to get all of the data at each temperature step, as the experiment's running, because this can only be done once. So we don't want to heat the sample twice because the result the second time is not going to be the same. Okay, so just one final example. So if we just look over on the right-hand side, this is an example of how the EELS spectra look. So these are some summed K3 spectra for oxygen K and copper L. And then we did some PCA noise removal, and you can see, this is the kind of the sharpness in the fine structure that we're getting here. And this is why we're able to do this oxidation state mapping and the LNES mapping of the oxygen K edge over this, big energy range. So just kind of in closing, this experiment was done with a 2 degrees temperature resolution. So 2 degrees Celsius temperature steps, we're getting EELS, EDS, then 40 STEM and EDS data at each temperature step. So what we end up with is 880 separate spectrum images in this single experiment. So Continuum IS, a new experimental paradigm for EELS and FTEM that enables you to make critical decisions after the data is collected. So we can capture dynamic behavior and support diverse users, techniques, and projects. So I just want to thank everyone for listening and see you next time.